Every time you write a line like this, something happens inside your computer's memory that most Java developers never actually see. Java creates an object somewhere. It stores a reference to that object somewhere else. And later, it quietly removes that object when nobody needs it anymore, without you ever calling free like you would in C or C++. So, where exactly does the object go? What does the variable S1 actually hold? And how does Java clean up memory all by itself? By the end of this video, you'll be able to look at any line of Java code and know exactly what's happening in memory. Let's open it up. Before we talk about Java specifically, let's define memory allocation in plain terms. Think of memory like a room full of shelves. Before placing anything on a shelf, you need to reserve space for it. That act of reserving space is memory allocation. Every program needs memory for variables, objects, arrays, and information about which method is currently running. Some of that memory is needed only for a moment. Some needs to stick around much longer. Java handles most of this automatically, but to see how, we need to separate two ideas: memory that's managed for you in stack frames and memory that's dynamically allocated in the heap. In lower-level languages like C, you'll often hear about static versus dynamic allocation as two formal categories. In Java, it's more useful and more accurate to think in these terms instead: stack-managed local data and heap-allocated objects. A simple local variable like intx equals 10 is automatically handled as part of the current method's stack frame. Java knows its size immediately, and it doesn't need anything special from you. Dynamic memory allocation is different. It happens at runtime, while the program is actually running whenever you create an object or array with the new keyword. Java doesn't know these details until the program runs. The array size or how many student objects you create can depend on user input or program logic. That memory is allocated in the heap. One important note: Java doesn't give you manual control over this the way C or C++ does. You don't get a raw memory address and you never manually free anything. Java manages it for you, which is exactly what we're about to see. Let's define stack and heap properly using this code. The stack stores the frames created for each method call. Inside main's frame, it also stores local primitive variables like age and reference variables like student. The stack works in last-in, first-out order. When a method finishes, its entire frame and everything local to it is automatically removed. The heap is different. It's where objects and arrays actually live. The heap is shared across your whole application, and objects stay there until they become unreachable, meaning nothing points to them anymore. We'll come back to exactly what that means very soon. So watch what happens. Age lives directly inside the stack frame, but student does not contain the actual student object. It holds a reference to where that object lives in the heap. One quick note: this stack and heap picture is the conceptual model Java developers use to reason about memory. The JVM may optimize things internally in ways you never see, but this model is the right way to think about ordinary Java code. Let's slow this down even further because the new keyword is doing more than it looks like. Step 1, Java allocates a block of memory in the heap, sized to fit a student object. Step 2, the constructor runs, initializing that memory here, setting name to Ahmet. Step 3, a reference to that newly created object is produced. Step 4, that reference, not the object itself, is stored in the variable S1. This is the single most important idea in this video. S1 does not contain the object itself. It contains a reference that lets Java find the object in heap memory. The object lives in the heap. The reference variable lives inside the current stack frame. Here's a moment that confuses almost every Java beginner. The line student S2 equals S1 does not create a new student object. It copies the reference. Now S1 and S2 are two different arrows pointing at the exact same object in heap memory. So when we change the object through S2, by writing s2.name equals Ravi, we're not creating a second separate Ravi object. We're changing the one object that both S1 and S2 point to. So when we print s1.name, the output is Ravi, not Ahmet, because there was only ever one object the whole time. Quick side note, for simplicity, we're focusing on the student object itself here. The string Ahmet, stored inside it, has its own special handling in Java through something called the string pool. That's a separate topic we'll cover another time. Arrays in Java are objects too, which means they also live in the heap. AR in the stack is just a reference. The actual array, 4 index slots, each starting at the default value 0, is created in the heap. When we assign a value into the first slot, we're reaching through that reference into the heap to update the cell. And this next line is where dynamic allocation becomes really obvious. We read a size from the user and then create a new array of exactly that size. The size of this array isn't known until the program is actually running and the user types a number. That's true runtime, dynamic memory allocation. Watch what happens when we reassign a reference. First, an amit object is created, and S1 points to it. Then, this second line creates a brand new Ravi object, and S1 is redirected to point to that one instead. Nothing else in our program still points to amit. No stack variable, no other object, nothing. Which means amit is now unreachable, and an unreachable object becomes eligible for garbage collection. Notice I said eligible, not immediately deleted. That distinction matters a lot, and it's exactly what we're covering next. Java automatically frees memory for you. You never call free or delete like you would in C or C++. Instead, Java's garbage collector periodically scans the heap, looking for objects that no active reference can reach anymore. Those objects are removed, and the memory they used is returned for future use. You can write the line system.gc, but it's important to understand what it actually does. It's only a request. The JVM decides when, or even if, it acts on that request right away. In everyday Java programming, you almost never need to call it, and you should never rely on it running immediately. In C and C++, you manually allocate and free memory, forget to free it, and you get a leak. In Java, you just write new, and the garbage collector handles cleanup for you. But here's something worth knowing. Java can still leak memory. It happens when an object is no longer needed, but something is still holding a reference to it, so the garbage collector can't touch it, for example, endlessly adding objects to a static list and never removing anything. Forever reachable, forever uncollectible. 5 quick myths busted fast. Myth: variables store objects. Truth: they store references. Myth: Java has no memory management. Truth: it's automatic, but object lifetime still matters. Myth: assigning one variable to another copies the object. Truth: it copies the reference. Myth: garbage collection is instant. Truth: it only makes the object eligible. The JVM decides timing. Myth: Java can't leak memory. Truth: it can if something keeps referencing what you no longer need. Let's tie it all together in one final walkthrough. Marks goes into the stack. S1 is created, an amit object appears in the heap, and S1 refers to it. S2 equals S1 means S2 now refers to that same object. No new object exists. S2.name equals Ravi changes that one shared object. Our array scores is created in the heap with 3 slots, and we fill them in. Then S1 equals new student Neha creates a brand new object, and S1 now refers to Neha, but S2 was never touched. It still refers to the Ravi object, so our output is Ravi, then Neha. And because S2 still holds that reference, the Ravi object is not eligible for garbage collection yet. It's still reachable. Let's bring it all together. Java uses dynamic memory allocation whenever you create objects or arrays with new. Local variables and method calls live in stack memory. Objects and arrays live in heap memory. Reference variables refer to those objects. They don't contain the objects themselves. Assigning one reference to another never copies the object, only the reference. Unreachable objects become eligible for garbage collection, and Java handles the actual cleanup automatically, but you, the developer, still need to understand how references work to write correct, bug-free code. Once you understand stack, heap, references, and garbage collection, Java objects stop feeling mysterious. You can actually reason about what's happening under the hood. In the next video, we'll connect this straight into array list and dynamic data structures, how they actually grow in memory behind the scenes. If this helped things, click, hit like, subscribe for more Java and DSA content, and tell me in the comments what memory or DSA topic you want explained next.